afternoon, everyone, or good morning, everyone, depending whereabouts in the world you are. As Rob said, my name's Ian Brooks. I'm the Technical Director at Additure. Additure are a division within Kingsbury Machine Tools Group, but the difference there is Additure is focused on manufacturing metal AM parts, and we operate laser powder bed fusion from SLM Solutions, and also WAM, so wire arc additive, from a company called DfAM in Berlin, and it's that latter technology that we'll focus on for this afternoon's presentation. Now, before we break into it, this isn't a sales presentation. This is aiming to be technical, really, to cut to the crux of what WAM's good for and indeed what it isn't good for. But in order to do that, there's a bit of a preamble that walks us through why Additure exists, why it's here, because it's all relevant and it puts everything into context. The other thing I'll say before we break into it, this presentation is punctuated by at least 3 videos plus some clips of the process itself, and that does 2 things. Firstly, it means you don't have to listen to me for 40 minutes, which we'll all be very thankful for. And secondly, I believe it really puts into context and really gets the message across quite well. You know, these were very well thought out video clips of different case studies as well as the process themselves. So without further ado, just a little bit of background into Kingsbury and its origins. Sound check, Rob.
There we go.
Excellent, excellent.
I'm often asked when Kingsbury was founded, and the straightforward answer to that question is 1956. But I think a more interesting question is why? What was it that got the ball rolling? And to answer that question, we need to go back a little further in time to August 1945 and the Potsdam Conference. An interesting link, and one that warrants further explanation. But in August 1945, the Allies had got together to discuss reparations at the end of the Second World War. And of course, by this time, Germany had exhausted itself financially, and therefore these reparations were to be levied in the form of intellectual property, plant and machinery, and land. And the reason I'm describing this is that the CAM auto manufacturer Index were very much caught up in this arrangement. And it was agreed that Index's design rights would be given to the machine tool division of the British industrial giant BSA. And that BSA would get to produce Index design machines and badge them as their own and sell them in the UK market and other markets around the world. And I think the reason that Index were chosen is that in the interwar years, Index had developed a burgeoning reputation for producing arguably the best CAM autos in the world. And to help illustrate this, I'm putting up 2 pictures for you to look at. The first is of the Index 25 CAM auto, and the second is the Rolls-Royce Silver Cloud. And the reason I've chosen these 2 pictures is that they have 3 common attributes. Firstly, I think they are both aesthetically pleasing, nice to look at. Secondly, they were very much considered at the pinnacle of their art. And the third common attribute is that they sold in the market at roughly the same price, at just over £2,000. At around the same time, just after the Second World War, my grandfather had a subcontract turning shop. And in that turning shop, he used both pre-war Index machines and also the BSA badged versions. And he quickly came to the realization that there was a disparity in the quality between the 2. He also learned during this period that this reparations deal was time limited to 10 years. And at the end of that period, Index would be free agents again, would have the ability to do what they wanted in the markets that they wanted in the way that they chose. And during this time, George decided that he would rather sell Index machines than use them in his factory. So he put a plan in place to try and make that happen, which also involved sending his eldest son, my father, Mike Kingsbury, over to Index with the mandate to win over the senior management team in Esslingen. And I think they were obviously quite successful in this plan, because at some time the sales director from Index was sent across to the UK to check out George and his company and to establish whether Kingsbury would be the right partner for them going forward. And as was the fashion in those days, they repaired to lunch somewhere in London. I believe it was Simpson's in the Strand. George felt that the discussions were going well, and it was then that he decided to play his trump card. And the trump card that he played was that were Index to give him exclusive distributorship of their products in the United Kingdom, he would write out a purchase order for 30 Index cam autos there and then. And we shouldn't forget that these cam autos were selling in the marketplace at exactly the same price as a Rolls-Royce Silver Cloud, so a sizable investment. But George would write out the purchase order for 30 cam autos on the basis that Index gave him 120 days to pay for them. Well, there isn't a sales director in the world faced with that proposition that wouldn't say yes. So the deal was struck. George went back to the office to inform his two boys that he just purchased 30 Index cam autos and that they had 120 days to sell them. And that's how Kingsbury started with Index back in 1956.
So quite an interesting story there. And that's how Kingsbury started, but how did we get to where we are today with Additure? We started with Index, then there was a period of reasonable growth, and then in 2003, they signed the exclusive distributorship of Hermley, so milling solutions in the UK and Ireland and the Gulf states. On the back of the success with Hermley in 2012, Kingsbury launched a large prismatic machining division with the players that you see there at the top. Over a three-year period, they onboarded at these organisations. Followed reasonably swiftly with a grinding division. And then most recently, from a sales perspective, we onboarded DfAM and SLM Solutions just before the pandemic. And then for the purpose of myself and the ongoing presentation here, Additure was founded in February of this year. There's been a more recent introduction with a company called DfAM that make large machine tools as well in November of this year. So why Additure? Why did a machine sales organisation launch what is a contract parts manufacturing service for Metal AM? So born out of frustration, we've been involved in Metal AM for many years. The potential market is confused, different technology coming out all the time. ROI, very hard to justify over conventional alternatives, and confusion as well. We strongly believe that the knowledge sharing in additive and the knowledge is retained by handfuls of individuals around the world, and that simply isn't scalable at the current rate. So very frustrated with the market, but again, mainly passion and determination. So we've seen firsthand what Metal AM can do for organisations and for applications. We're determined to accelerate the adoption of Metal AM. So the initial concept of Additure was, to put it bluntly, a try before you buy service. Let's get people over the line and get them investing in the technology, first with people from a knowledge sharing perspective, and then invest and prove the ROI and invest in the CapEx. I'm Ian Brooks. I'm the technical director at Additure. I've been involved in AM for 12 years now. Previous to that, I was a manufacturing engineer in aerospace and automotive, primarily with large prismatic machining. Most recently, my focus has been on AM. Here at Additure, we have two technologies. We have laser powder bed fusion, arguably the most common Metal AM technology, and we have wire arc additive manufacturing as well from DfAM. Additure was born out of a passion to push AM out into the industry. We're conscious that the business cases are difficult to justify. Often the components are hard to realise. So it's born out of a passion. We've seen what AM can do for businesses and organisations. We've seen the benefits that it can bring, and we really want to springboard that out into the wider sectors and out into industry en masse. We want it to be able to be judged on its own merit against other manufacturing technologies as well. So out of the R&D world, and really ask the questions, can this manufacturing engineering technology stack up against conventional? And indeed, where does its niche? For each of the different technologies, where does its niche fit? So this is our location as well for Additure. So we're up in the north of the UK. roughly in between Manchester and Liverpool, and not actually just a stone's throw away from Nick Weeks at Carpenter, actually, but not so far from Nick at all. So we have laser powder bed. I've put the most common there, and it is in terms of an install base and use. It certainly gets the most hype around it. It's the most difficult to justify in terms of an ROI, and that's mainly due to the last point there. So to really realise the opportunities, you have to put that effort into the design stage up front to make your application have a performance improvement in some way or another. Kind of contrary to that is wire arc additive. It's been around for a while, based on well understood technology, but the install base is far lower, orders of magnitude lower currently. We operate industrialized equipment from DfAM. What I mean by that is that you can buy a black box solution. It's not an integrated solution where you buy a robot arm from somebody and a software tool set from somebody else. They offer an end-to-end solution there. And for the most part, with the components for WAM, the ROI is far easier to justify. They are far more benign parts. They're not, algorithmically designed rocket thrust chambers. They are everyday brackets and hubs and rib type structures and things. But the big advantage there is we build parts that exist now. We don't have to do the redesign piece. So the proposed journey there between Additure and Kingsbury starts with process development, then some knowledge transfer. Jumping on from that, then, there's a commercial, let's justify the commercial benefits. There's the ongoing knowledge share as well from consultation. The CapEx then has to be justified at some point, and then there would be a machine purchase via the Kingsbury Group at the end. We also recognise that along this journey, there will be clients that simply don't manufacture components. They don't want to invest in the CapEx, and there is a model and an outlet there for Additure to continue that ongoing contract parts manufacture. That's kind of the background now. So just hooking into a little bit of the WAM technology. I've assumed a base level of understanding of what WAM is throughout this, and I'll cut through this quite quick, and we're going to focus on really the applications, because for all these technologies, be it polymers or metals, they will in the end be judged on what they can do for users. So what manufacturing challenges can they solve? So the system you see in the middle here is the ARC 403, 405 variant from DfAM. It's the smaller one of two variants. So I think from memory, it's about 700 mil in the X by 1100 in the Y and 1500 mil in the Z direction. The configuration that you see there is the five-axis configuration. So the table in the middle there is a rotary and trunnion axis. That can be removed, and you put down a three-axis table as well. It's owned primarily by the Berlin Industrial Group. On the right-hand side, you can see some of their other departments as well, the largest of which, in terms of revenue and people, being Scansonic, who make optical systems, galvanometers and such. So at DfAM in Berlin, and they're all part of the same campus. They share some common resources, all these groups, but they house an R&D function, product development, engineering, and it's an application and a sales center as well. So why WAM? Lots of different technologies, new technologies every day under the AM banner. So why WAM? What is it good for? Now the sales pitch would be reduced inventory and reduced lead time, and that's quite simplistic. Clearly, there are applications where you want to reduce your inventory and lead time that simply would not be beneficial to produce by WAM. So when we assess components and we assess applications, it's far more nuanced than that, and we have to break it down. And this is how we do it. A series of 5 questions that will give us an initial insight into whether it is a goer for WAM or not. So the first question is it a high value component? So upwards of £1,500. Is it a high value material? So not a mild steel, you know, duplex steel, titanium, nickel alloys, tool steel, something like this. Can the base plate form part of the component? So like all 3D printing and AM technologies, the time spent is laying down the material. So if you can minimize that, you also minimize your cost per part. Fourth is it large? Upwards of 20 kilograms. And then the fifth one is a real kicker. Is it easy to qualify? And I know different perceptions of easy exist, but I suppose what this is all about is it low-hanging fruit to qualify, you know, this component in your sector? And we don't judge this on the basis that we need 5 yeses. I think from experience, we've found that if you have 3 or more yeses for these, then you're somewhere in the right ballpark to have, you know, a good sound WAM application, and it's worth exploring. What this is all about, and what I must say at this stage, is all the AM technology are tools to solve a problem. And for many years, people have been trying to use laser powder bed to solve conventional problems that can be solved conventionally. We've overcome that now, but let's focus the technology on what it can do best, and not waste our time and waste our clients' time on things that we don't believe it's good for. So we're very focused on the problem that we can solve, and indeed whether we should be solving it with what we have. And we will be the first to admit if we're not the right technology. So I've got a couple of examples to share as well, where we went through this process of defining whether it was a good application or not. So on the right hand side, you have a part. I can tell you that part's called a futule. It's an obsolete part, or it was an obsolete part. There was no CAD or 2D drawings for that. To give it some sense of scale, it's 1.2 meters long, so it's a large part. It's part of a ceremonial gun. There was no current manufacturing pathway, and it was mild steel. So if we compare that with, you know, our questions and we go through that kind of mantra of ours, yes, it is high value. It's an obsolete part. It's needed. These are low numbers, so that the cost is going to be significant. No, it's not a high value material. Yes, it absolutely can. So all the bottom bit that you see there, you know, we will only add the outside rib that you can see. It is large, and you won't know, but I can tell you it was reasonably easy to qualify, you know, on the grand scheme of things. So we've got our 4 yeses. So there is no noise to this, by the way, so it's not an issue. What you can see here is the WAM process itself on the futule part. This was actually completed on one of the large Kiefertech platforms, the ARC 603, and it'll run now. You can see the nozzle there for extraction. It's a MIG CMT process from Fronius, so the process gas is coming down the center of the torch there. The deposition rates are high, certainly when you compare it with laser powder bed. We would quote 4 kilos an hour. That is geometry dependent, mind, and it does depend a lot on the cooling rate. In between layers, there's a pyrometer that will ensure that the temperature is cooled to approximately 150 degrees before the next layer commences. And I will just skip on a little bit on this video because it is quite long and it does repeat itself. As I mentioned, this was quite a simple geometry. We did the outside rib. The middle of the part there is just a base plate that we procured. Little image of it being machined. We do have milling capability at Additure. We didn't have a machine that was big enough to take this, so this went out into one of our customer bases. Still machined on a Hermley, though, I may add, but on a larger platform. And the finished part as well. And what I can say that is pleasing with any AM application is this did go into active use. So it's a real part. There was a qualification campaign, as I mentioned. It was reasonably benign on the grand scheme of things, but it was qualified. It was manufactured, it was measured, it was built to a standard, and it did go into use as well. So the other example is this part on the right-hand side. There is a case study in the form of a video that I will play after this slide, but if we go through our kind of mantra again, yes, it was high value. Yes, it was a reasonably high value material. It was a low alloyed chromium, molybdenum, nickel steel. Yes, it did, not as significant as previous, but it did. It is large and high mass. Not as easy as the other one, but there are varying degrees of easy, as I say. So for this part, it was an absolute winner, and there was some more reasoning as well why this made good sense for WAM. And I'm not going to issue any spoiler alerts there because there is a follow-up case study.
As the world becomes more aware as to the potential of additive manufacturing, I'm reminded of the situation back in the 70s when the first numerical controlled machines were introduced to a skeptical market. For decades, the CAM Auto had been providing lightning-quick turning capacity across all sectors. In comparison, the early, ponderously slow, single-turret, single-spindle NC machines left many an engineer scratching his head as to where things were headed. And whilst in many cases, cycle times have still not eclipsed those of the CAM Auto, in high labour rate economies, these machines are now nothing but museum pieces, a testament to the ingenuity of man. The same transitional processes are now happening within additive manufacturing, as it transforms into a viable economic alternative to subtractive machining. And this video seeks to tell that story. A story that describes the needs-driven journey of the rail sector giant Deutsche Bahn as it faced the difficult situation of an urgently needed part that was going to be delivered on a 10-month lead time through the normal process of casting and then subtractive processes. In this film, we have recreated that journey, documenting the processes undertaken and interviewing the decision makers who made it happen.
My name is Florenz Lichte. Together with a colleague, I'm managing the implementation of additive manufacturing at Deutsche Bahn. The secondary roll stop is a heavy steel component bolted underneath the car body of a frame. It's an operation critical component that secures safe cornering of trains in tight curves. It's a part that we normally don't have on stock because it's not meant to be replaced during the regular maintenance schedule. But in this case, we had to fix an accident repair on our ICE fleet, and we had a demand of 2 parts. So we had to get them quickly. We got a quote from our supplier offering 4 parts minimum order quantity. But the downside was that we would have to wait 10 months for the casted part. And we would have to pay some serious money for the initial tooling costs. And you might imagine that was not an option for us. We had to reduce the downtime of the vehicle drastically to get it back into service quickly. And so we said, why don't we print this part? Why don't we use the wire arc additive manufacturing technique to manufacture these 2 parts? And that's what we did. We set up a cooperation quite quickly with Gefatec and Wolf Lenk, who manufactured the part. And in the end, we were able to prove that we could reduce the lead time of the part by 5 months. 5 months, and we could lower the total costs by 30%. Today, we are progressing quite well. We've printed over 15,000 parts so far, 200 different parts, from small plastic parts up to 27 kilo steel parts like the secondary road stop. So quite a progress.
Deutsche Bahn identified a part with a very small demand and approaches us if it's possible to realize this part in a 3D printing process instead of a conventional manufacturing process. Hello, my name is Tobias Krimberg. I'm CEO of DfAM. DfAM is a Berlin-based technology company. Founded in 2015, we are focused on metal 3D printing by using DfAM technology, or as we call it, 3DMP. 3DMP stands for 3D metal printing, containing the CAM software, containing the process, containing the machine, and containing the quality management. The advantages of using 3DMP for a high-value metal part production is that you can reduce the cost of the entire produced parts, you can reduce lead time, and you can increase availability. And by doing this cooperation, we realized that we have here a real business case. So we grouped together with the Deutsche Bahn, was focusing on the entire process, what is needed to bring this part into industrial usage. So that means the printing, the process from the technology side, but as well the qualification. And we did it very successfully.
I'm Kevin Hawley, Director at GOM UK. So GOM supply 3D scanning metrology equipment from manual systems through to fully automated systems. And in terms of component sizes, this can be from something small you'd hold in your hand through to complete car bodies, and all of those sizes of components are measured on a daily basis. So to create the scan data for a Deutsche Bahn part, we took the CAD model, we put it into our software where we've got what we call a virtual measuring room, so a virtual environment. And once we've placed that in the rotary table of the scan box, the software will take care of most of the hard work and create the scan positions for us. We received the component around lunchtime on the Friday, and for the WAM part, I think the scan process was complete within an hour or so. If you've got some fantastic time savings from building your part on something like a DfAM, then it makes sense not to waste any time further down the process. So by scanning, we can understand the part geometries and ensure that will clean up when it's being machined. For reverse engineering, if there was no CAD model available for a Deutsche Bahn part, that process in terms of data capture would be exactly the same as what we complete for the inspection of the WAM part. So within 30 minutes to an hour, you would have all the scan data you need to reverse engineer that part from. The data that GOM supply Kingsbury will allow them to optimize the machining process on the Hermle, so avoiding any air cuts and ensuring that the net shape part produces a perfect finished machined part.
Hi, my name's Dan Castles and I'm Business Development Manager here at Kingsbury's for Automated Solutions. In this stage of the process, we take the 3D welded part and we set it up onto a 5-axis CNC machine. In this case, we're going to be putting on the Hermle C650. The initial phase of the process is to plan a method and program the part. By utilising the scanned image from the GOM machine at this stage, rather than a theoretical stock, we can optimise the tool paths to the exact form of the welded part. Therefore, we don't have to do any safety passes, or there's no chance of overloading the spindle on a heavy cut. The Hermle solution sits well with the whole process, so the DfAM welds the part, then goes onto the GOM machine, which scans the geometry which has been welded. They then take that STL file and we load it into our CAM system and use that as our stock. There's no way of doing this without a 5-axis machine in one hit. The beauty about our machine is we have a slender spindle design and a very large A-axis range, which enables us to get into part geometry which are very tight to get into. The Hermle C650 is a perfect platform to machine the final stage of the Deutsche Bahn roll stop.
In the interview with Herr Lichter from Deutsche Bahn earlier in this film, he described how when faced with a 10-month lead time from their normal conventional route of supply, they looked at an alternative way of making this part. Their pursuit of a DfAM solution effectively reduced that lead time, cut it in half. But it's important to note that this was the first time they'd gone down that route. So there was a lot of investigation and development and design of processes before they could realize the completed part. In this film, what we've tried to do is reproduce that journey. That's involved the filming of the part in 3 different locations. So we printed the part at the DfAM facility in Berlin in a cycle time of 36 hours. We then shipped the part to the GOM facility in Coventry, where we did the scanning. And then finally, we brought that built part, now having scanned it, back to Gosport, where we machined it back to net shape on a Hermley 5-axis vertical machining center. The cycle time for the machining was around the 7-hour mark. So in reality, what was a 5-month process when it was done originally is now something that we could bring down to a matter of days. Wire arc additive manufacturing, or DfAM, allows for the rapid deposition of material in the building process. It takes place within a machine that is kinematically arranged around 3 or 5 axes, depending on specification, all of which is controlled by a Siemens 840D controller. The raw material used is standard welding coil. An important point to emphasize: arc welding was first developed in the 19th century. We all rely on it in our everyday lives, be it in the car that we drive, or as we have seen, the train that we commute with. It is a fully understood and accepted manufacturing process, and because the raw material is welding coil, as opposed to metal powder, does not require the same health and safety precautions associated with a powder bed fusion machine. If your current processes involve the lengthy lead time of hard-to-machine material, be it cast, forged, or billeted, then this solution from DfAM may prove to be an interesting commercial alternative. We hope you have enjoyed this video and that the insight that we have given you provides an idea of how the DfAM solution could be a commercial option worth considering. Many thanks for your attention.
And that brings me to the end of my slide deck. But just to summarise, what I would say is at Additure and Kingsbury, we are 100% focused on solving manufacturing challenges. In order to do that with the equipment that we have and the technology that we have, we first have to find what those challenges are and ensure that the technology that we have can indeed solve those problems. They aren't panaceas for all manufacturing challenges. You know, powder bed has its niche, as does DfAM, you know, as does some of the other technologies. But very, very important that we as an industry and we as users find what those problems are as quickly and efficiently as possible. And it's then that we have the business case, and all the other problems, well, they disappear then. So thanks very much for your time, and I will hand you back to Rob for the Q&A.
Thank you very much, Ian. That was a really, really interesting presentation. And he's good as Richard, isn't he? He does a good video. I think he could do more documentaries about his experience. I really like it.
He was called the David Attenborough of engineering, so that's what I'm up against. You know, it's a tough act to follow.
Yeah, well, they've just done that new video today. He's not in, and I'm sure it'll miss out having me and you on that. There is a couple of bits in the chat. So there's somebody looking for some contact details. I'll let you respond to that one. Okay. There is a question about oxidation in WAM. So how do you prevent oxidation in WAM? And I think I'll push you a little bit more on that about, you know, you look at what goes on locally in terms of shielding. I think it's worth explaining, but then bigger picture in terms of control of a larger part, global heat levels. How do you avoid oxidation, but also nitrogen, hydrogen embrittlement?
Yeah, it's a difficult question. So thanks for that, whoever it is. And it's somewhere where this is where the industry academia stuff would really kick in. You know, as is the focus of today's forum. So there is localized shielding on the machine. Depending on the material, we can have a global shielding as well. Is it fit for purpose? Yes, in some instances, but I would say it's all horses for courses. So some parts have different cross sections than others, and those parts will operate with a different trailing heat thermal distribution than others. So I'm not going to say it's finessed. There are other providers there that have specific localized shielding nozzles as well. I think it's an area of research, I would say in a nutshell, to simplify my response on that. We can manage the heat input a little bit. Like I mentioned, we have a pyrometer on board that won't allow us just to keep putting heat in and heat in and heat in. There's localized cooling in the table. We have done things in the past with the fixturing, so we can produce fixtures with induction heating and things. What this does is adds a lot of cost if you're making a 1 or 2 off part. So we really need to get over this and have other control mechanisms that are scalable for the batch sizes that we're talking about. But yeah.
No, I think that's great, and like you said, that kind of is the point of the forum today. Is let's do some of these things and trials. I presented some of the initial results of the pip testing we did on the one parts that
I missed that as well.
Yesterday. So
yeah.
I'll send you those. They're quite interesting. But it was very late. We had some issues with YVDM, but the chemical analysis, the opportunities. I made a note and I fired it off to a professor at Bolton before, listening to Nick about embrittlement. Quite often will show surface strain. How sensitive is a photo stress camera? We've got a photo stress camera. How sensitive is that to pick that up? Is that an area of exploration?
Yeah.
And hopefully there's lots of people listening who've got access to other equipment that I maybe don't know exists, or you don't know exists, or we wouldn't know how usable it is. And if we can bring that together, that does allow confidence to build. Richard put it very well. We have been using arc welding for many years. We haven't been using it for major structures. We've tied structures together, so it is subtly different. And I think all we need is confidence.
I think it's the kicker with all AM technologies is you're making the geometry on the material at the same time, and that's what makes it cool, right? And that's what gets everybody in this virtual room, because it's interesting. But it's also that makes it scary from a quality point of view. So we would never overlook the need to ensure that the material is appropriate. It's the second question we ask. So it's why would you use this technology? Where's the business benefit? And then how are you going to qualify it? So what is that process? Do you understand that this is a new material and a new microstructure, etc.? So yeah, not something that can be overlooked.
And I'm sure Richard and Jason, who are the next 2 speakers who've got on, will have something in this general field. This is not a unique issue for a key protect system. This is certainly something which I think Richard and Jason will also have views on, and I'm sure that will come up. Final call for any questions. I'll ask one quick one while we wait and see if anything pops up in the chat. We talked quite extensively there on WAM, and there's lots of research opportunities. What about with your SLM equipment? Is there any low-hanging fruit that you'd like support with, or any areas that you're certainly keen to hear more on? If anyone in the audience has got some experience with thing X, Y, or Z.
So it's everybody's favorite R&D topic, isn't it? Laser powder bed, because it's a gold mine of topics. I think the feedstock control and reuse strategy is more important than we ever gave it credit for. So we operate an aluminium here, and the risk of moisture pickup within that system is significant, and the impact of which is only just really starting to be quantified. Other than that, I really like the new approaches from different software companies that shall remain nameless, that are looking to hand the power over to the user with regard to toolpathing. So for years we've been stuck in this. I used to call it Magic's blind, because we've been really entrenched in the use of Magic. So we take an STL, we can do certain things with it, but then we hit go and it hatches and slices it for us, and it gives us an output, and we have limited input on how it does that. So we don't know what's going on under the hood, and we certainly can't control it. I think we could get huge benefits there if we could control toolpathing more, and there's various ways we can go about that. But from a productivity and a quality point of view, I think there's a lot of potential there, and we would happily engage with people on that score. So if anybody has free or access to Autodesk licenses that also have the advanced toolpathing utility, then we're all ears. What that allows you to do is code your toolpath line by line. So, you know, that's really the goose that laid the golden egg for us.
Yeah, and you know, if anyone doesn't know, any academic institute will get free access to NetFab Premium, and you can make requests for NetFab Ultimate. My request went in last week, and was approved. So I think it's worth looking at.